So if you tried to do this using the squeeze theorem, like as we learned it yesterday, then you would have started it and you would have been like, oh, sine theta is between -1 and 1, right? That's how you would have started it. And then you would have been like, oh, let me divide by theta, right? And then if you plugged in 0 for theta, you can't do anything. So the squeeze theorem, as we did it yesterday, does not work for this problem, okay? And that's why we have to do a special proof. Can you remind me what I'm giving you? Optional proof? Okay.
Thank you.
Okay. All right, so instead of doing it this way, we're going to go ahead and do it using pictures. It's going to be pretty exciting. Okay, so here's the first one. We're going to draw the same angle on all of these. So I'm making it like approximately 45 degrees. But just make that angle the same on all of these. Okay, and right here, I'm going to drop this down, and I'm going to find the area of this triangle right here. So this almost references like a unit circle where this is a coordinate x, y, right? And if I wanted to find the area of that triangle, I would say 1/2 times the base times the height, right? Okay. And so over here, except the base isn't 1. Hold on 1 second. Well, let me think about that. Sorry. That was a good label, but we're actually going to find the triangle we're finding. I didn't notice my drawing is a little bit different. This is the triangle. Go ahead and draw that line right there. It's not curved, it's straight. So the angle is still correct. This part right here we dropped down is still good. This would be like the height of the triangle. Does everyone see that? And so you still have this part right here, which is like a right triangle, and you're still thinking of this point as like x and y, okay? And this part right here is like x, but that's just till that length. This part right here, which is also the height of the triangle, is kind of like the y value, right? We go to the right x and up y, and that's where that point comes from, if you think about how the unit circle like comes together. Okay, so if I want to think about this as 1/2 times the base times the height of the circle, I'm going to say 1/2 the, sorry, not of the circle, of the triangle. The base of this triangle would be a length of 1 if we're talking about a unit circle, because a unit circle always has a radius of 1. That's how it got its name. So I'm going to say 1/2 times 1. And then for the height, we have that y value, right? And y, the y coordinate on a unit circle stands for what? Anyone remember what it corresponds to? Thinking trig? Sine. So I'm going to say, instead of using y to represent the height of this, I'm going to say sine theta. Okay? And that's because sine theta is exactly the same thing as y. So at this point, we are finding the area of this whole triangle right here, and we are representing the area of that whole triangle using this expression. 1/2 times the base of 1 times the height of sine theta. Okay. All right, in this one, we are going to find the area of the entire slice. We call these sectors, right? Because we've got that curved side right there. And to find the area of a sector, you may or may not remember this from pre-cal, depending on who your teacher was for pre-cal and what they taught you. But to find the area of a sector, you do the theta that you have divided by 2 pi, and then you multiply that by the area of the circle. So if the whole area of the circle is pi r squared, then theta out of 2 pi would be saying that's like the portion of the circle that I want to keep the area of. And so what we'll notice here is that this pi and this pi will cancel out. And we're going to get theta divided by 2 times r squared for that expression. Make sense? Okay. And then over here, we're going to draw a right triangle, but it's going to go outside of the circle, like this. All right, now if I'm finding the area of this whole circle, or sorry, triangle, I have, again, 1/2 times the base times the height, right? And then what's the base still? 1, because we're still thinking unit circle. So I'm still going to have 1/2 times 1, but now I need to get an expression for the height. It's not going to be y like last time, so it can't just be sine theta. But if this is the theta I have, this would be the opposite side and this would be the adjacent side, right? And the opposite is what we're trying to determine the length of. The adjacent side we already know the length of. That's why I'm using those two sides, okay? And what does opposite and adjacent make you think of? SOHCAHTOA, but what is opposite and adjacent specifically? Tan, okay. So I'm going to say tan theta equals opposite over adjacent, except I know that the adjacent side is actually a length of 1, right? The adjacent side is actually a length of 1. So for this specific triangle, not always, but for this specific triangle, the opposite side is going to be equivalent to tan theta. All right? So the height of this triangle is tan theta. Now, if you compare the areas of the triangles, this area is the smallest, this area is the biggest, and this area is sandwiched between them. Agree? Okay, so I'm going to add my inequality symbols. All right, now we did all of these in the first quadrant, so we know that our theta right now would be like a positive theta. It would give us positive values if we plugged it in, but if we would have drawn it in a different quadrant, those signs would get all messed up. So what we're going to do to show in our proof that these values have to be positive is we're going to put absolute values around all the pieces that have thetas in them. And that's going to make our proof work regardless of the quadrant that we're in. We good? All right. So I'm just going to clean it up a little bit. I'm going to say sine theta over 2 is less than or equal to, what's the radius of this circle? Yeah. 1. So for this one, I'm just going to say theta over 2 because we know that radius is 1. And then for this one, I'm going to say tan theta over 2. Okay. So at this point, we can kind of think of the squeeze theorem the way that we did it yesterday.
Yes, Ms. Brian Smith, have Nancy after dismissal, please. Thank you.
Cool. So if we look at this, we're thinking now in terms of like the squeeze theorem, how it was. So now our goal is to get sine theta over theta in the middle. All right, because we want to squeeze this. So what could I do to start getting closer to that goal? Yeah, I'm going to get rid of the 2's, right? Okay, so I'm going to say sine theta is less than or equal to theta, which is less than or equal to tan theta. And then what could I do? Yeah, I would divide by sine. Why would dividing by sine be better than dividing by theta? because then you can do the flip thing. Okay. So if we divide by sine, then that means we're almost there. I was squinting after that because I was trying to think if it would work or not. I was like, did we get back there? Okay, so what do we have over here? 1. Here we have theta over sine theta. This one's taken me back to pre-cal a little bit. So we've got tan over sine. How could we fix that to simplify it? It's sine over cos, right? Over sine over 1. We could flip it up. So what does it give you? 1 over cos? Okay. All right, and then at this point, what should we do? Flip everything. What happens when we flip everything? We change the signs. So we're going to say 1 is greater than or equal to sine theta over theta is greater than or equal to cos theta. Okay. So we got what we wanted in the middle. Now what do we do to find the solution? So we're going to say the limit as theta goes to 0 of 1 is 1. And then over here, the limit as theta goes to 0 of cos theta is 1. And so that means that this limit is 1, yeah. And this is a special limit, like you can use this property to do a bunch of other problems, and so this is one that people memorize. This would be like something you wouldn't want to forget because you can use it to make other problems more simple. Okay, go ahead and take this sheet of paper and flip it over. Yeah. Yes, so this would be a situation maybe where you hadn't learned L'Hopital's yet. This is like, we would have learned this in the first unit before we taught you guys how to do L'Hopital's. And that was one of the reasons why I wasn't really worried about not teaching it to you guys, is because L'Hopital's would work. Yeah. All right, one of the other things, and we can write it at the top here, is that if this equals 1, then that would mean that the limit as theta goes to 0 of theta over sine theta would also equal 1. And you can see that if you don't do the part where we flipped it, if you, this part right here, if you take this part before we flipped it and find the limit as theta goes to 0 here, that's 1. The limit as theta goes to 0 here is also 1. And so the squeeze theorem would have worked right here if they wanted that version. Okay? So both of these equal 1. That's something that you'll keep in mind. Okay? All right. On the other side of your page, this proof is a little bit more difficult, but it doesn't use pictures like that one did. This is like the other special proof, and let me look just to make sure I don't write it down wrong. I used a lot of paper on there. It is 1 minus cos x over x. This is another one. This is like another special one that people memorize. Okay, so with this one, the trick is to kind of get it back so we get some signs in it, because sine x over x is the one that we know equals 1. So what they do for this one is they take this fraction and they multiply it by the conjugate of the top. What's the conjugate of the numerator? Anyone know what a conjugate is? Opposite sign, yeah. So it's 1 plus cos x. And so what does that give you on the top? 1 times 1 is, and then we got plus cos x and minus cos x, and those cancel. And then minus cos squared, okay. And then on the bottom we have x times 1 plus cos x. I did not distribute the x for a reason, you'll see in a little bit. What is 1 minus cos squared? Sine squared. Okay, so the limit as theta goes to 0 of sine squared okay, and then here is how they finish this proof. They manipulate things a little bit. So what they do is on the top, instead of saying sine squared, we're going to think of it as 1 sine times another sine. And we have that x, and we have the 1 plus cos x. And what I'm going to do is on the top and the bottom, I'm going to multiply by x, and you'll see y in a second. So this right here, the limit as theta goes to 0 of sine x over x would be 1. We just figured that out, right? And the limit as theta goes to 0, I should have been using thetas this whole time, but yeah, sorry, my bad. And then this one is also 1, right? And so we can ignore these basically. We wouldn't say they would cancel out. We're just going to say that these two limits end up being 1. So when we want to find the limit overall, we're going to ignore those two pieces and we're just going to look at the leftovers. So what happens if you plug in 0 up here and 0 down here? What do you get? 0 over 2, which is 0. So the other limit that we kind of like learn / memorize is this one, that 1 minus cos x over x equals 0. That's like a special proof. So I think the first one, the sine one, is more common to like have the answer memorized too. I think this one, but this proof is kind of obnoxious too, so I think, anyway, those are like the two special ones. So if you take out your worksheet from yesterday and then flip it over to the back side, the side we didn't work on, then it has problems that are like this. Yeah?
It says recall that the limit is x goes to 0 of sine of x over x equals 0.
That's a typo. I meant 1. Sorry. Did you guys like that typo? Wasn't that a fun typo? All right. No, you're good. What is the first problem on there?
Limit as x approaches 0 of sine 5x over x.
Okay. So if we use the idea of what we just learned, then we know that the limit would be 1 as long as the angle that's inside of sine is the same as what you have on the bottom, right? So this would equal 1 if I had 5x and 5x, right? But I don't have a 5x on the bottom. So what I need to do to fix this is I need to multiply this by 5 on the top, and I need to multiply it by 5 on the bottom. All right, and then I can say this part would have a limit of 1 because it's sine 5x over 5x. And then I can do direct substitution to finish out the problem. So it equals 5. Yeah. All right, what's the next one?
Limit as x approaches 0 of sine 3x over sine 2x.
Okay. So for the sine 3x on top, what do we need to have on bottom? A 3x, right? So I'm going to put a 3x on bottom, but whatever I do, I have to do it to the top and the bottom. Okay? For the sine 2x on the bottom, what do I technically need to have on the top? 2x. So this part right here has a limit of 1. And then this part right here has a limit of 1. And then what can we do? I would cancel the x's. And then I would say 3 over 2 is my limit. Interesting, huh? It's just a neat little trick. Okay, so I'm going to let you work on those. They get more difficult, so there's some where it starts to like throw other trig functions in there. But your goal is to always bring it back to either the sine x over x or x over sine x, or bring it back to 1 minus cos x over x, because those are things that we know. So if you can manipulate the problem to have one of those, then you can say that part of the problem has a limit of 0 or part of the problem has a limit of 1, and then you can work with the rest of the problem. So that's kind of the goal. And that's what we're doing today. Ta-da! Isn't that fun? Yes, Miss Rice? Marvelous.